5.4. Okay. Just pay attention, guys, and this is a very, very important section. They call it the backbone of statistics. This is the foundation of statistics, what we are going to learn, because how do we use samples in statistics? But because of the availability of technology, it used to take me, just an hour to explain, this theorem to students. But now with the presence of technology, you're going to see it's going to take me a few minutes, because you're going to be observed, you're going to make observations, and your observations are going to be the result, of this theorem, what we're going to try to do right now. So you can see, guys, that you have a bell-shaped distribution right here. The mean is 25 and the standard deviation is 5. I could change it if I want, but I'm just going to leave the 25 and 5. They're nice numbers. And look what we're going to do now. We're going to collect samples of size 9. So the size of each sample is 9 items, 9 data values in each sample. How many samples we're going to collect? We're going to collect as many samples as we can. So I'm going to collect 1 sample. And what this applet is going to do, let's say, guys, I want to survey students' age in my class, and I'm not going to pick all 30 students. So I pick 5 students, and I'll try to figure out, the average age of those 5 students. So what I can do to do the average, just add up the 5 ages and divide by 5, I get the sample mean, which is called the sample average. And this applet is going to do the same thing for the sample. So for each sample, this applet is going to find the average of each sample. So if I pick 1,000 samples, it's going to do 1,000 averages. If I do 10,000 samples, it's going to do 10,000 averages. And it's all before even you blink your eyes, guys. It's all going to be done in the background. And we're going to ask the applet to do a histogram, of those values, and we're going to see what shape we're going to get. So I'll pick 1 sample. See, 9 values are being selected, and then the mean will be calculated. And look where the mean is put in green. This is the mean. So if you add up those 9 values, guys, and divide by 9, you get this number right here. Let's do another one just to see it in action. You see, no 2 samples are the same, guys. Randomly picked, you get 2 different means, and they call them the sample means, guys. Watch the sample means. Now I'm going to do it 1,000 times. So we picked 1,000 samples, and we asked the calculator to find the mean of each sample. So I got 1,000 means. Look, guys, this is 1,000. Let's do it one more time. Another time. I got 3,000. And you see, guys, it's all happening in the background, being processed. It doesn't even take to blink your eye for this. I'm going to do 10,000 samples. So I did 10,000. You can see it, guys. Number of samples, 10,000. You want to do 11,000? We can do that. There you go. 13,000 samples. Okay. Now I need your participation, guys, please. So here we have the original population, and here we have a histogram, a graph showing 25,000 sample means, 13,000 sample means. You can see here, 13,000 and 2. I'm going to ignore the 2, guys, 13,000 samples. Okay. Can a student remind me what was the mean? What's the mean of the original population? You can see, guys, it's 25, but I like you guys to look at the mean of the sample means. What do you notice? What is it? What's the mean of the sample means? Who can tell us?
25.
25 again. Look, the original one has a mean of 25. And then when you pick samples, guys, and you find the mean of each sample, and when you pick a large number of samples, look at the mean, 25.0007. I mean, 0007, you can ignore it. If it is a dollar amount, 0.0007 is nothing. So it is 25 again. Okay. Which graph, guys, has a larger standard deviation? Is it the black one, which is the original population, or the samples one, which is the sample means distribution?
The black one.
The black one has larger because it's more spread out. Okay. What is the standard deviation, guys, of the original population? It says it's 5. What is the standard deviation? Look at the standard deviation of the sample means. It's narrower. Guys, the narrower, the better for us when we study statistics. That means there is not much variation amongst the data values, and that's very important in statistics. When there is so much variation, your results are skewed, just you cannot have reliable results. But when you are working with the data where the results are very close together, the values are close together, it's better. So look at the standard deviation, it's 1.6734. Here is what I like one of you to do now. There is a connection actually between 5 and this one. The sample size, we said it's 9. So I like you to do this, guys. I like you to take the 5 and divide it by the square root of 9 and see what you get. And I'm gonna pause the recording for now. I like, just to reset this one. Just one sec. Okay, it doesn't matter. Let's make it size 18. And let's do 1,000 samples. 2,000, 3,000, 4,000, 5,000, 6,000, 7, 8. See, with technology, I can do as many samples as I want. Okay. Look, guys. The mean of the original population is 25.2147. Look at the mean of the sample means 25.23, which is pretty close. Now, I would like you to take this standard deviation, 5.3134, and divide it by square root of 18 and see what you get. 5.3134 divided by square root of 18. Okay, I got 1.2523. Look, guys, at the standard deviation, 2535, which is very, very close, approximately the same. But we notice that the distribution of the sample means is bell-shaped with a smaller standard deviation, but the same mean. They both of them get the same mean. Okay. Now we're gonna take a population that's not normal. It's skewed and see if the same thing will happen as we noticed before. When we had a normal population, guys, we got the mean of the sample means to be the same as the original population, and the standard deviation is smaller, and the sample means look like bell-shaped as well. Well, this is not bell-shaped. Let's see when we draw samples what happened. But this time I'm gonna change the sample size and make him 30 or more, guys. So more than 30. Let's make him 36. And I wanna do 1,000 times. I'll do 10,000 samples. Okay. Here you go, guys. What is the mean of the sample means, guys? 94.88. What is the original population mean? 94.88 if you round to 2 decimal places. No changes, guys. Even if the population is skewed, when I draw samples, I still get the same mean. That's big one thing. Do you notice, guys, that the distribution of the sample means still look like bell-shaped, which is very important to us in statistics. We only can work with curves that are bell-shaped. All the properties and the formulas we come up with in chapter 5 are based on the fact that you are working with a population that is bell-shaped. So this is bell-shaped. Now I like you to look at the standard deviation, guys. It is 14.5608. I would like you to divide it by square root of 36. What would you get, guys? 5608 divided by square root of 16, which is 4. You get 3.6402. Oh, 36. I divided by 6. Sorry. My miss. 5608 divided by 6. Okay, I got 2.42. And look, guys, at the standard deviation, it's 2.42. Okay, let me change this one to a sample size of 100. And draw, and now I'm going to change this one, guys. It'll be done in a second. I want to make it good. Right. Okay. There you go. That doesn't look bell-shaped. The mean is 90.72 and the standard deviation 14.87. What happens when I draw a sample, large samples, and whether the new sample means will look bell-shaped or not? Watch, guys, they should. I'm going to do 10,000 samples. Okay, watch, guys. The original mean of the population was 90.72. Look, this is 90.73, which is pretty much the same. Now, guys, I like it to take 14.87 and divide it by square root of 100. What is a square root of 100? It's a 10. So if you do 14.87 divided by 10 will be 1.487. And here you get 1.5, which is pretty much, just very close to it. So actually the sample means whether your population is bell-shaped or not bell-shaped, they will still have the narrow bell shape. Their standard deviation is lower, and the mean would remain the same as the mean of the population. Meaning, guys, it's always good to work with a sample because samples are accessible. We can collect samples, but we cannot survey the entire population. And on Monday, when we meet in class, I'm going to show you guys how to do applications and what we learned. It's not going to be any different from what we have done so far. We'll be using the normal CDF function, but working with samples instead of individual values. So that would be what we will be doing on Monday. And since I did not complete this one and I didn't do applications on what I just discussed, is called the